questions 8 through 10 on the 2010 grade 12 Euclid math contest. Oi Lam tosses 3 fair coins and removes all of the coins that come back heads. George then tosses the coins that remain, if any. Determine the probability that George tosses exactly 1 head. So we make a table, right? The first is when he or she, I'm not sure Oi Lam is male or female, I apologize, tosses 3 fair coins. Now, what are the possible ways of getting our results when you toss 3 fair coins? Well, you can have all 3 are heads. We can have heads, heads, and tails. And there's 3 sort of arrangements for that as follows. You can have 2 tails. So heads, tails, 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 heads, tails, 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 heads. Or you can have all 3 tails. Okay, so the first 3 coins have these possibilities. And each of these, of course, has an equal probability of happening. They're all 1/8. Now, we get into George. Now, George has a different sort of scenario. What he does is he looks at the coins that were initially tossed, and if anything comes up heads, he removes it. So in the first scenario, he's going to have 0 coins remaining, right? Because they all turned up heads, and he removes coins that turned up heads. In the second scenario, he's going to have 1 coin remaining. 1 coin here, 1 coin here, here 2, 2, 2, and here 3. Okay? Then what he does is he flips the coins that he has remaining, and we want to know what is the probability that he gets exactly 1 head. So only 1 head. So not 2 heads, not 3 heads, not at least 1 head, but exactly 1 head. Okay, well, let's talk about that. And the simplest way to do that is just by listing the possible ways that it can happen. If there's 0 coins, well, there's nothing to discuss. This is nothing. Okay? If there's 1 coin, well, 1 coin can end up either heads or tails. So the probability of getting exactly 1 head, well, it's just half here. Half is the probability of getting exactly 1 head. So these ones are pretty straightforward. They're all the same. Heads or tails, and the probability of getting a head is a half. Now we get into 2 coins. If there's 2 coins, we've got the following scenario. You can have HH, HT, TH, or TT. Okay, all of these are the same. Now, let's discuss this. Of these 4 scenarios, how many involve exactly 1 head? The only ones are this guy and this guy. So it's 2 out of 4. And 2 out of 4 is really just a half. So again, we've got a half. Now we get to the last one. The last one, its scenarios are exactly as this, right? Because we have 3 coins. So instead of listing them all here, they're already here. They don't need to be listed again. We just have to look at which ones are exactly 1 head. Exactly 1 head are this guy, and this guy. So 3 of the 8 possibilities. So 3 over 8 goes here. Now we have to combine all these probabilities. So how do you do that? Well, you have to multiply this number by this number, this number by this number, and so on, and then you add them all up. So for the first one, it's 1/8 times, well, there's nothing here, right? It's 0. So that doesn't count. You don't even need to count it, really. The next one, of course, is 1/8 times a half. But to save ourselves some time, there's so many of them, right? There's 6 of them that are identical. So it's really just 6 times 1/8 times a half. And then the last one is different. So it's 1/8 times 3/8. And that is our probability. So P for probability, it looks like, let's see here, 6 over 16 plus 3 over 64. And getting a common denominator, that's going to be top and bottom here by 4. So it's going to be 24 plus 3, 27 over 64. That is the answer to this question. In the diagram, points B, P, Q, and C lie on the line segment AD. The semicircle with diameter AC has center P, and the semicircle with diameter BD has center Q. The two semicircles intersect at R. If PRQ is 40, determine the measure of angle ARD. The first thing I'm going to do is connect some lines. So join B to R and join R to C. And now we have to identify a few things first and foremost. If you recall, if you have any kind of semicircles type situation, for example, if you have a circle and then you have a semicircle like that, any angle that you draw that fits within that semicircle like that will be 90 degrees. So that's a very important aspect of this question. Another law that exists is that if you have a line from the center and you draw a line to one edge like that, and then you compare angles, this angle right here, if it's x, this angle will be 2x. So we are going to incorporate those rules on this triangle. These triangles, I should say. So now let's start labeling a few things. ARB, this angle in here, I will call A. BRP, I will call B, this angle in here. PRQ, that one they give me is 40 degrees. QRC, I will call C, and CRD, I will call D, and that way I can start making some equations. Now, let's identify this type of a scenario in our big diagram. Do we have any kind of triangle that fits exactly into a semicircle? And the answer is yes, we have actually two of them. The first one is this one right here, from A to R to C. That one. This whole thing will be 90 degrees. So that basically means that A plus B plus 40 plus C is equal to 90. So from that we get A plus B plus C is equal to 50. Is there another such 90-degree angle? And the answer is yes. This one, from B to R to D, that one. Those angles combined to give 90 as well. So that means that B plus 40 plus C plus D is equal to 90. So that means B plus C plus D is also equal to 50. Okay? So now we want to take advantage of this law, that x and 2x. So in particular, we're looking at this angle and we're looking at that angle. So if this angle is x, this angle will be 2x. Okay? But instead of writing x's, I can consider the fact that we've got a couple of isosceles triangles. And in particular, this one right here. This triangle APR is isosceles. Why is it isosceles? Because this side, A to P, represents the radius of that big circle because P is the center. And this P to R also represents the radius. So this is the same as that. And therefore, this angle has to be the same as that angle. So since that angle is A plus B, this is also A plus B. Okay? And then now using this rule, this angle in here must be twice this angle. So instead of A plus B, we write 2A plus B. Okay? So one more isosceles triangle. This time concentrate on BQ. That is the radius of the smaller semicircle, and so is QR. That's also a radius of that smaller semicircle. So that means this is the same as that, and therefore this angle is the same as this angle. So that angle is B plus 40, so this is also B plus 40. So now good news is we're in the final stages of this question. Now we have to look at a triangle BPR. So this triangle right here, BPR. And in that triangle, we have to add up the angles. Well, this angle I just wrote is B plus 40. And then the other angle in BPR is just B. And then this angle in here, that one I haven't labeled, but I know it's 180 minus 2A plus B, because remember, the sum of the angles about a line equal 180. So that angle is 180 minus 2 times A plus B. And all of that is equal to 180, since the sum of the angles of a triangle equal 180. So let's multiply this all out. This becomes 40 plus 2b. The 180s cancel on both sides, minus 2a minus 2b, and that equals 0. So the 2b's cancel, so I'm just left with 40 is equal to 2a, and therefore a is equal to 20. So that's a very important result. Now, finally, let's calculate ARD. ARD, so A to R to D, all the way there. All of those angles, all right? So that looks like it will be ARD is equal to A plus B plus 40 plus C plus D. Now we just figured out was 20. B plus C plus D is right here, right above it actually. Don't have to look too far. That's 50, and then plus this 40. And 20 plus 50 plus 40 is 110. 110 degrees is the measure of angle ARD. If theta is an angle whose measure is not an integer multiple of 90, prove that cotangent theta minus cotangent 2 theta is equal to 1 over the sine of 2 theta. To prove this, of course, we need a few trigonometry identities and definitions. Some of these are a little bit easier than others. Cotangent, of course, as you know, is 1 over tan theta. And tan theta, of course, you know, is just sine over cosine. And then a couple more that you need to refresh your memory. Sine of 2 theta, that one is 2 sine theta cos theta. And the tan of 2 theta, I think we will need that one, is 2 tan theta over 1 minus the tan of theta squared. So hopefully this is all we need to prove this. Now, like any proof, we got to write it in a way so you have right side and left side, and then they have to match. So this is, of course, our right side right here, and this is, of course, our left side. Now let's see what we can do. I'm going to start with the left side first. Left side looks a little bit less complicated. So left side is just going to be equal to 1 over sine 2 theta. What sine 2 theta is 2 sine theta cos theta. And I think that's it for now. I don't think I can go any further there. So that's it. If I can get my right side to look like that, then I'm done with my proof. So now let's concentrate on the right side. Well, cotangent is 1 over 10. And cotangent of 2 theta, well, that would just be 1 over tan 2 theta. And at this point, we can get a trigonometry identity to help us, and that's this one right here. So we're basically just going to flip that. Since it's already in that form, I just flip it. So 1 minus tan theta squared all over 2 tan theta. And this is relatively simple to add, since all we have to do is just multiply top and bottom by 2 to get a common denominator. So this just becomes 2 minus 1 plus tan of theta squared all over 2 tan theta. Okay, so this becomes 1 plus tan squared theta over 2 tan theta. Now at this point, my left side had sines and coses, right? So let's, instead of having tans, let's put in sines and coses. So tan squared, of course, is sine squared theta over cos squared theta. And I've got this 1. But instead of writing 1, I'm just going to write cos squared theta over cos squared theta so I can add that fraction. Basically, I'm just getting a common denominator. And then again, this is pretty straightforward, sine theta over cos theta. Okay, let's bring this up. So the top becomes sine squared theta plus cos squared theta, or cos squared theta plus sine squared theta, like that. And all over cos squared theta. And it's all over 2 sine theta over cos theta. Now, cos squared theta plus sine squared theta, I hope you remember, this right here equals 1. So that's what it just boils down to. And then I'm going to invert and multiply. And if I invert and multiply, I get cos theta over 2 sine theta, like this. Now at this point, one of these coses cancels with one of these coses. So all you're left with is just 1 over cos theta times 2 sine theta. And if you rearrange this a little bit, you get 1 over 2 sine theta cos theta. And that is exactly like the left side. So left side, or sorry, I should say, well, I seem to have mixed the left side and right side. It doesn't matter. Basically, forget about these RS and LS. Just know that this side, which is right here, I was able to make it look like this side, which is essentially over here. That's the same as this right here. So, as you can see, this proof is pretty straightforward. It's might look a little daunting in the beginning because you've got cotangents in there, but if you convert them to tan, it's actually not so bad. Ross starts with an angle of measure 8 and doubles it 10 times until he obtains 8192. He then adds up the reciprocals of the sines of these 11 angles. That is, he calculates sine of 8 reciprocal plus 1 over sine 16 plus 1 over sine 32 dot 1 over sine 4096 plus 1 over sine 8192, and that is equal to S. Determine without using a calculator the measure of the acute angle alpha so that S is equal to 1 over sine of alpha. In this question, you may notice that it's 9a part 1 and part 2. They don't even write 9a and 9b. They just stick with 9a and make a part 1 and a part 2. Now the reason I'm emphasizing that is because part 1 leads directly into part 2. And in particular, you're going to be using that to solve part 2. And if you can, realize that, it makes your life a lot easier. So here we go. For this S, we have 1 over sine of 8, right? But if you use this, that becomes the cotangent of 4 minus the cotangent of 8, right? Exactly what is here. No tricks. Just substituting 8 for 2 theta, and therefore it would become cotangent of 4 minus cotangent of 8. Now let's do the same thing for the next one. If you do, this time 2 theta is 16, so it becomes cotangent of 8 minus the cotangent of 16. Now let's do the next one, and hopefully you'll see a pattern. This is going to be the cotangent of 16 minus the cotangent of 32. And then you just keep going like this until you get to the last one, which would be the cotangent of half of that. So that's 2048 minus the cotangent of 4096. And then the very last one would be the cotangent of 4096 minus the cotangent of 8192. Now, hopefully you've seen that this cancels with this cancels with that, and it keeps on going like that. You notice this cancels with this right here. Everything cancels. So all you're left with at the end is the cotangent of 4 minus the cotangent of 8192. So as you can see, this formula that you just proved in part 1 is extremely helpful because this is great. Now we still have a little bit of work to do. We're not home free because S is 1 over sine of alpha, and they want you to figure out what is alpha without using a calculator. Now what you have to notice is that in any trigonometry value such as sine, cosine, they all have certain periods, right, where they keep repeating. Wanted to show you the graph of cotangent of x to illustrate a point that you notice is exactly the same every 180 degrees. You see, this is pi, which is basically 180. It's exactly the same. And what that means that cotangent of anything, whether it's x or alpha or theta, it has a period of 180. And therefore, the cotangent of anything is the same as you go in multiples of 180. So if you take this big number and keep subtracting 180, it will give you the same value. And if you do that, you can easily do that in a calculator. You can bring this 8192 by subtracting 180, 180, 180 all the way down to just 92. And since cotangent is periodic in this nature, cotangent of 92 will be the exact same value as cotangent of 8192. So that makes our life very much more manageable in this question. So now we continue, and then we can just change cotangent to its sine and cos. It's basically just the reverse of tan, right? So this will be cos of 4 over the sine of 4, and this will be the cos of 92 over the sine of 92. Okay. Now at this point we have to use some trigonometry identities that are definitely going to help us out. And I'll write those identities. Some of you may remember these, but they're worth repeating. Cos of theta is equal to minus sine theta minus 90. And then another one is sine of theta is equivalent to the cos of theta minus 90. So use those, we get, this one doesn't change yet. We're going to keep this for now. But this one we can get much more manageable numbers yet again by using these. Cos of 92 becomes minus sine of 2. And the sine of 92 just becomes the cos of 2. So as you can see, that's much more helpful. Now we have 2's and 4's. We want everything to be the same. Well, I hope we can make everything the same. And therefore, let's just remind ourselves of the double angle identities. Sine 2 theta is 2 sine theta cos theta. I think we used that earlier. And the cos of 2 theta is equal to 1 minus 2 sine squared theta, like that. So this will help us. Therefore, this becomes 1 minus 2 sine squared theta, but it's not theta, it's 2. And then the sine of 4 becomes 2 sine of 2 cos of 2. And this we can just put plus sine of 2 over the cos of 2. And then now we can get a common denominator. Let's see here. It will be multiplying top and bottom by 2 sine 2. So this will be 1 minus 2 sine squared 2. If you multiply this guy top and bottom by 2 sine 2, it becomes 2 sine squared 2. And then everything is going to be 2 sine 2 cos 2 in the denominator. And some great things happen in the numerator. Those two cancel. So all I am left with is just 1 over 2 sine 2 cos 2. And then flipping it back, using this to kind of bring it back, it would be 1 over the sine of 4. And let's not forget, this whole thing was 1 over sine alpha. So therefore, alpha is equal to 4. And that is what they wanted for this part of the question. In triangle ABC, BC is equal to A, AC is equal to B, AB is equal to C, and A is less than 1/2 B plus C. Prove that the angle BAC is less than 1/2 of the sum of angles ABC and ACB. We have some triangle. We can label it ABC, and they have told us that the sides are small a, small b, and small c. And they have given us a few hints that the sides have this inequality, that a is less than 1/2 BC. And these are the sides. But they want us to prove something about the angles. And using just A, B, and C, the large letters, we have to prove that angle A is less than 1/2 the sum of angles B plus C. And that, of course, is talking about the angles. Now, the angles of any triangle, if you have them A plus B plus C, denoting the three angles, they, of course, add up to 180. So B plus C, if you were to isolate, would be 180 minus A. So this one right here, we can further work with it by substituting in this 180 minus A. And if we do, we get 1/2 times 180 minus A. Multiplying that out, we get 90 minus A over 2. Bring the A over 2 to the other side, and you get 3A over 2 is less than 90. And therefore 3A is less than 180. And dividing through by 3, you get A is less than 60. So we essentially have to prove that A is less than 60. I just took their original inequality and brought it down to here in a perfectly valid way. So if I can prove that this angle is less than 60 degrees, I have proven what they want. So how are we going to do that? We will do it with the cosine law. But before we get started, let's see what we can do with that inequality that is a given. They have told us that A is less than 1/2 B plus C. So since this involves the sides, we can try to manipulate this. The first thing, of course, multiply through by 2, and you get 2A is less than B plus C. Now, if you recall, the cosine law involves A squared, B squared, C squared, that kind of stuff. So I want to get it to help us, so let's change that into squares. You can do that by squaring both sides. That would become 4A squared is less than B squared plus 2BC plus C squared. And at this point, I don't think I can go any further with that, so now let's start with our cosine law. Our cosine law on that triangle ABC would give us a squared is equal to b squared plus c squared minus 2bc cos of angle A. Now, what we can do is substitute this into this inequality. So instead of 4a squared, I will write 4, but a squared is this big long thing, b squared plus c squared minus 2bc cos A. And that is less than, according to this inequality, b squared plus c squared plus 2bc. And let's multiply this out, and we got 4b squared plus 4c squared minus 8bc cos A, and that is less than b squared plus 2bc plus c squared. At this point, we have to substitute something that is what you call a technique, or a trick rather. Since this is less than that, it will also be less than something else. Like, for example, if I put 5, it will still remain valid because this is not an equation, it's an inequality. So, for example, if this, let's say, this whole thing was equal to 3 and this whole thing was equal to 4, 3 is less than 4. But if I add something, the inequality remains true. 3 is also less than 9. So we have to take that into consideration, that we can add something without worrying about changing the inequality. It will remain valid. And what we're adding is a algebraic trick, 3 times bc squared. And this is going to be a positive because you're taking the square of a number. So it's going to be greater than 0. So that's why this inequality is true. Now that's a difficult trick, I think, but that's why it's number 9 on the grade 12 math contest. So if you put this in and you multiply it all out, you get the following. And once you multiply it all out and you collect like terms, you will see a lot of things will start canceling. So this side remains the same, but on here we get 4b squared plus 4c squared minus 6bc. And if you notice, this b squared, this b squared, this c squared, and this c squared cancel. So all of those go, and the only thing you're left with is this minus 8bc cos A is less than minus 4bc. Now the bc's cancel, and therefore cos A, remember, we have to flip this now because we've got two negatives and we're dividing through. So it becomes 4 over 8, which is 1/2. So the cos of A is greater than 1/2. And if you make a little sketch of the cosine graph, right, this is 1 and the half is right here, and the value that corresponds to that on the graph is 60 degrees. So if we want the cos of A to be greater, that means that A must be less than 60 degrees because the angle A is acute. So we don't need to worry about anything that's anywhere else on the graph. And therefore we proved it. Remember, we wanted to prove that A is less than 60, and that's exactly what we've done. So the proof is complete. For each positive integer n, let t at n be the number of triangles with integer side lengths, positive area, and perimeter n. For example, t at 6 equals 1, since the only such triangle with a perimeter of 6 has side lengths 2, 2, and 2. Determine the values of t, 10, t11, and t12. Well, let's just talk about this briefly. If you have any triangle with side lengths A, B, and C, using the triangle inequality, A plus B must be greater than C. That's the only way a triangle can be made. Now they're telling us that the perimeter of the triangle A plus B plus C is going to be equal to n for any t at n. And using our triangle inequality, A plus B has got to be greater than C. So we can combine these. If A plus B plus C is equal to n and A plus B is greater than C, that means A plus B plus C is greater than C plus C, right? Because I just took this, put it there, I added a C, and then this is the C, and then I added the C on that side. That's all I did. So that means that you have the following. This is equal to n, so n is greater than 2c, and therefore c is less than n over 2. And in a very similar way, we can also create another one, inequality, that is, that in any such triangle, if we rank them from smallest to largest, we can say that A is less than or equal to B and B is less than or equal to C. They could all be equal, and they've even given you such an example. But generally speaking, they would be less than or equal to. And therefore, again, considering the fact that they all add up to n, that basically means that A plus B plus C is going to be less than or equal to, A is less than or equal to C, B is less than or equal to C, and C is just C. And then this guy is n, so n is less than or equal to 3c, and therefore c is greater than or equal to n over 3. So if you combine these two that I just figured out, to give that c is greater than or equal to n over 3, but it is less than n over 2. Okay, so that is what we're going to use to figure out T10, T11, T12, like that. Now, you can do it the long way, but this way is just a little bit more structured, that's all. So let's start actually with T at 9. I know T at 9 is not asked for, but I'd like to calculate that just as an introduction. Well, A plus B plus C, in this case, the perimeter, is 9. And using our little inequality that we figured out over here, that means if C is one of the side lengths, it's going to be between 9 over 2, which is 4.5, and it's going to be greater than or equal to 9 over 3, which is 3. So C obviously can be either 3 or 4. So if C is 3, for example, there's only one way of making this 3, 3, 3. You'll notice that you have to keep this triangle inequality always in mind when choosing values for A and B. If C is 3, A plus B has got to be equal to 6, right? And the only way you can get two numbers to equal 6 and maintain this triangle inequality is 3 and 3. If C is equal to 4, that means A plus B this time is equal to 5. And the only way to maintain the triangle inequality is to have 1, 4, and 4, or 2, 3, and 4. So that means for C equals 3, I got one such ordered triple, and for C equals 4, I got 2. So this is 1 plus 2, which is 3. All right. So we're going to do the same thing for these ones. I just wanted to give a little brief introduction with a relatively easy one. And T at 10 and T11 and T12 shouldn't be too bad. So in the same way, A plus B plus C is equal to 10 here. So that means C is going to be between 5 and 10 over 3. So that's what? About 3.3. So that means C is going to be either 4 or 5. Actually, only 4 because it can't be equal to 5. It's less than 5. So c equals 4 is our only value. That means a plus b is 6. And let's see what we can get to maintain this triangle inequality. I think A, B, C, the only ordered triples would be 2, 4, and 4. And 3, 3, and 4. I think that's it. So we got t at 10 is equal to just 2. There was only 2 that we got. And keep going like this, t11. And this time a plus b plus c is equal to 11. And therefore c is going to be less than 11 over 2, which is about 5.5. And greater than or equal to 11 over 3, which is approximately 3.6. So c has to be equal to either 4 or c has to be equal to 5. If c is 4, that means a plus b has to be equal to 7, and the only way to get a triple satisfying the triangle inequality is 3, 4, 4. If c is equal to 5, that means a plus b is equal to 6, and that can be satisfied in a few ways. We can get 1, 5, 5, 2, 4, 5, and 3, 3, 5. So here we got 1 here for c equals 4, and we got 3 for c equals 5. So t11 is equal to 1 plus 3, which is 4. And finally, we've got t12 to figure out. So we got t12, and in the very same way, a plus b plus c is 12. So that means c is between 6 and 4. So c can only be either 4 or 5. If c is 5, that means a plus b is equal to 8. And the only way to make that work is 4, 4, and 4. Any other combination would not satisfy the triangle inequality. For c equals 5, a plus b is 7. And the only ordered triples that work are 2, 5, 5, and 3, 4, 5. And there you go. We've got for t12, 1 here and 2 there. So t12 is equal to 1 plus 2, which is 3. So t10 is 2. t11 is 4. And t12 is 3. And we also figured out that t9 was 3. So that takes care of part A. Part B. If m is a positive integer with m greater than or equal to 3, prove that t to the 2m is equal to t to the 2m minus 3. Now to prove that, I'm going to call t to the 2m over here to have a set of triples. And those set of triples, of course, are going to be of the form ABC. And then t to the 2m minus 3 will be a set of triples over here. And I kept these two, t9 and t12, in the same screen because these behave like t2m and t2m minus 3. In particular, when m is equal to 6. When m is equal to 6, t to the 2m becomes t12. And t to the 2m minus 3 would be 12 minus 3, which is t to the 9. And you notice they both equal 3. And if you look at their ordered triples, they're very similar. 3, 3, 3 is very similar to 4, 4, 4. It's just one difference. 1, 4, 4 is very similar to 255. There's only one difference in each of those numbers. And similarly, 234 is very similar to 345. It's just one difference for each integer. So I want to show that if we have this in this set, that if you get something that has one integer less, namely a minus 1, b minus 1, and c minus 1, this is part of the set in Tm minus 3. Okay, so how do I do that? Well, over here, the perimeter a plus b plus c is going to be 2m, correct? That's what these ordered triples have to add up to. And over here, a minus 1 plus b minus 1 plus c minus 1, if you add them up, it's a plus b plus c minus 3, and a plus b plus c is 2m from here. So it's 2m minus 3. So there we go. It matches. We have shown that this, if we take one less for each value, it will be in this set. Now I also want to show a very similar thing, that if we have a, b, c over here, that if I take those values and add 1, that they will also end up in that set. So a plus 1, b plus 1, and c plus 1. Well, let's see. A plus b plus c over here, since it's part of this set, is got to equal 2m minus 3. And if you add these guys up, a plus 1 plus b plus 1 plus c plus 1, it becomes a plus b plus c plus 3. And this part is 2m minus 3. Then add 3, and that is just 2m. So that does indeed mean that it's part of that group, since the perimeter is equal to 2m. And if you notice, each of these is the same. When you take these and add 1 to each, 3, 3, 3, it becomes 4, 4, 4. If you take this and add 1 to 1, 4, 4, you get 2, 5, 5, and that is indeed in order triple. And same thing with this, if you add 1 to 2, 3, 4, it becomes 3, 4, 5, and that is an ordered triple in that set. So this is a very brief version of the proof, and in particular what we're really trying to show, that they have corresponding triples. So you can see that any triple in the set t to the 2m has a corresponding triple in the set t to the 2m minus 3. Either a, b, c corresponds to a minus 1, b minus 1, c minus 1, or a plus 1, b plus 1, c plus 1 corresponds to a, b, c. And finally, part C, determine the smallest positive integer n such that t to the n is greater than 2010. What we want to do in this part is look for any kind of pattern, because obviously we have to extrapolate this to get a very large number, much greater than what we've done so far. So if you just look at a few of them, and I'm going to concentrate only on the odd ones, because they seem to have somewhat of a pattern. Let's look at the first few. T11, and let's look at about 7 of them. And just like how we had calculated T9, T10, T11, T12 earlier, you can calculate these. And I'll write it out in the way I had written it before, which was in this format, where I was adding 1 plus 2 and 1 plus 2 like that, where I was breaking it up into how many triples I got for each value of c. If you do it that way, the pattern looks a little bit more clear. For T11, 1 plus 3 is 4. That is how many you get. For T13, it's 2 plus 3 for each value of c. For T15, we get 3 values of c, and therefore it's 1 plus 2 plus 4 for each value, and that totals 7. T17, 3 values of C. For each, we get 1, 3, and 4, respectively. And that gives me 8. For T19, 3 values of C. And you get 2 plus 3 plus 5 is equal to 10. T21, you get 4 values of C. That means 1 plus 2 plus 4 plus 5 for each value of C. And then T23, you get 4 values of C. For the first one, you get 1 ordered triple. For the second value of C, you get 3 ordered triples. For the third value of C, you get 4. And for the fourth value of C, you get 6 ordered triples for a total of 14. Now, this may not look like much of a pattern, but I will explain what kind of pattern is emerging. Basically, T at n, these numbers, are approximately equal to the sum of the integers from 1 up until n divided by 4. But you notice 1 out of every 3 integers is removed. So it's not 1, 2, 3 up here, it's 1, 3. It's not 1, 2, 3, it's just 2 and 3. It's not 1, 2, 3, 3 is gone again. Here the 2's gone, and here the 1's gone, and so on, right? So we have to somehow figure out, what does this mean for us? How do we get an equation? It's really just going to be approximate, and thus T at n is going to be approximately, since there's 1 out of every 3 integers missing, that means the other 2/3 are going to make up the sum. So you guys remember the formula for adding up sum of consecutive numbers from 1 to n, right? It's n times n plus 1 over 2. So if we're adding up the integers from 1 to n over 4, it would be n over 4 times n over 4 plus 1 over 2. But we're saying that it's approximately 2/3 of that, since 1 out of every 3 integers is removed. So we have to multiply this by 2 over 3. And that is a very approximate calculation for t to the n. Definitely not exact, but approximate. And since it's approximate, we can approximate even more and just have 1/3, and we can just get rid of this 1. And again, we're doing this approximation. It'll be n squared over 16, and combining it becomes n squared over 48. So this is a very approximate calculation for t to the n. By no means is it exact, but it helps us because we want something that gives t to the n greater than 2010. So that means we can put n squared over 48 here, and that's going to be greater than 2010. So n squared will be greater than 2010 times 48. And if you take the square root, you will get approximately that n is greater than 310. But this pattern that I just did up here was only for odd integers. So we can look at odd integers in the vicinity of 310. So we can start with 309, and then we can go up to 311 and take it from there, just to be on the safe side. And when you calculate t to the n, when n is 309, you get t to the 309 is equal to 2028, and that is indeed greater than 2010. So the answer to this question is 309. And then the painstaking process to calculate t of 309, I will show you. Here is the official solution, calculation of t to the 3009, and you will see at the very end it is 2028, which is indeed greater than 2010. So it's basically the same sort of story. You got to figure out c, and then for each value of c you have to calculate how many ordered triples there are, just like I did before for much smaller values like T10, T11, and T12.